Everyone, so I'm back again with another video. This one is on Van Heel's level of geometric thought and different stages of geometric thinking for children. What I have observed in my own teaching, and I believe you as teachers may have also observed, is that children are very confused and they're not very confident with different concepts of geometry. And in fact, much of the complexity comes when they have to go to more abstraction and prove it. So, what exactly is the thing that really inhibits them or maybe confuses them? The very act of proving appears to be very complex for them. So, Van Heel, so this is that video we'll be taking on his theory, and it's quite a very general and popular theory. But we can revisit the same theory, and I hope that you apply this theory in your classrooms and do see phenomenal changes in the whole understanding of students. A little bit about this theory. It is a stage theory and it's sequential. So every stage has a sequence to it. It's kind of a linear theory. So once one stage is achieved, then we move to the next stage and then to the next stage and then to the further higher and abstract. And it moves from simple, more concrete evidence to a more abstract form, as is true for most of the theories of learning. So we'll start right away. Uh, so as I mentioned earlier, that children have very different and confusing understanding about geometrical concepts. And you can take any possible concept. So just ask them what it means to them. Uh, in this example, I've taken what is a square. So these are the responses that I got from children. And somebody thinks that it's a quadrilateral with four sides. It has four sides. It has four sides and four right angles. Four equal sides and four right angles. A polygon with four sides. A regular polygon which has four sides. Now, interestingly, if you see in all of these examples, different children make very different sense of what a square is. And we can see that a child with this understanding or meaning of what a square is making a very different idea of what a square is compared to the last person who has a little closer to the right thing. In fact, it's the most accurate definition we can have of a square. It's a regular polygon which has four sides. So we see that when we probe a little deeper into children's thinking, we understand and realize that they come with so many variations of this very concept, and a lot of those variations are actually wrong. So I'll take another example. This one is from Google. So I was just searching what quadrilaterals are. The pictures are there was too many pictures on the board, but I actually wanted to capture the screen. So this is the whole page, the first page that I got when I typed types of quadrilaterals. As you can see from picture here all the way up to here, we are able to see only concave polygons, convex polygons. Uh, if we see in this one, this is the only concave polygon that we see. So as a result, what we see, even Google, the page of Google, it may have acknowledged, but look at the number of examples it has taken of convex polygons, convex quadrilaterals, and of a concave quadrilateral. So what we see is that the visualization children make even through these digital platforms is very limited. So they do not indulge with a lot of these examples, and as a result do not form an abstraction and generalization, which is very important. So I have taken the concept of congruence of triangles because I believe this is one of the very fundamental concepts of learning geometry. It starts somewhere for our school children. It starts in class 7, goes all the way till class 10, and it has more applications in grade 11 and 12 and even later. So we'll just take the stages, Van Heel's stages, and try to see how we can teach congruence based on these different levels of geometric thinking. A little bit about Van Heel, because we are discussing his theory, it will be injustice to not talk about him. So he and his wife, Dina Van Heel, they were Dutch researchers and teachers, and they themselves struggled and saw while teaching that children struggled a lot with problems on geometry. So they wanted to come up with a stage theory where they can actually identify the levels in which a child understands and forms a meaning of geometric concepts. So this originated at the University of Utrecht in 1957. Now I've taken the first stage. The first stage is called basic visualization and recognition. So we can see here that we have, you can pull this a little in the front. So we have a lot of these shapes, and the first stage is basically we just guide them as to what are the shapes which look similar to you or which are exactly same. So with that in mind, let children observe these properties, or this very informal understanding, and try to sort out things based on that. So they may match the color, they may match triangle with triangles, they may match square with square, or whatever thing they feel they can do that, and they're in this stage they're exploring a lot of properties. We can make it more explicit, saying that okay, match the things or select the things which are exactly same. So in that case they may come up with something like, if we are directing them to congruence, that selecting these pieces to put them together, and just using very informal strategies to find out if they're congruent or not. After this stage, once they have recognized, it's basically just a perception that they are forming, and they use very simple language which is not a lot mathematical. It's very common layman kind of a language that they use. The words are quite general. In the second stage, we've taken some example. In order to describe what congruent triangles are, children may use their own words. For example, they fit with each other, they overlap, they cover each other, they look same. The same can mean something like size or color for them. So it's up to them what kind of meaning they are forming. That's the first stage. In the second stage, we are now making it more explicit. Teaching is going a little more explicit, and we are actually analyzing the whole process. So in this case, if we can again come back to these shapes, uh, then also asking, okay, do you think that they have the same size? How do you know that? This side, do you think this will be equal to this side? What happens when you will place this side on this side? What are sides? What are angles? All these basic geometric properties about this are discussed. So it is more about describing what they are observing. For example, I've taken certain things. Also, in this stage, one important factor is that there is no difference for children in a necessary and a sufficient condition. Now, a very layman example is, to be a father, it is necessary to be a man, but not sufficient. So, similarly, in mathematics also, there are certain necessary categories and certain sufficient conditions also. If you take the example of congruence, all sides being equal, it's a necessary condition. All angles are equal, necessary condition. They should have equal perimeter, necessary condition. But they are not sufficient. If all angles are equal, it may be true that they may be similar but not congruent. So these conditions are all necessary conditions. Some of these conditions are also sufficient. For example, the first condition, if we see, all sides are equal, that's also a sufficient condition. If we see in a triangle that all sides are equal, if you are comparing two triangles, all sides of this triangle are equal to all sides, corresponding sides of the other triangle, then these two triangles are necessarily congruent. They will overlap each other, completely coincide with each other. Then two sides and the included angle is equal. I've taken one of the criteria of congruence. So this is a sufficient condition. But at the second stage, children are not able to differentiate between the two. For them, a necessary condition may appear to be a sufficient condition. Now the third stage is abstraction. They are forming informal deductions. What kind of deductions? For example, if the triangles are, let's say they are congruent, then the angles are equal. And for that they may be using protractor or anything to just measure them. So at this stage it is guided a lot by empirics and experimentation. So they may be actually measuring the side of the side or the angle. So it is a lot experiential even at this stage. They are still forming deductions, they are forming mental abstraction, but it is still confined to the physical object, and they measure things still around it. They give simple arguments to justify their conclusion. For example, if we take this square, although I don't see a square which is exactly congruent to this one, so they may say, okay, a square will always be congruent to a square. So these are informal deductions. It's not sufficient, but these are the kind of deductions they are making. For example, I've noted some of these examples. I'll move ahead. This is now the final. We are moving a lot more towards the formal mathematics and the formal deduction. So in this, they are understanding what definitions imply. I'll just share this example. Yesterday I took of what these transversal is, and I got very interesting answers, ranging from a line which intersects two lines to a line which intersects two or more lines, or a line which intersects, to a more finer understanding where it means that a line which intersects two or more lines at distinct points. So the children start to appreciate, and we as facilitators can also play a very significant role in helping them to understand the importance of making these definitions. They understand why axioms are there. They understand how from using these axioms we can derive certain theorems. So all the entire structure of how it is, they tend to appreciate that, also understand at a level. At the final stage, it is about rigor. Now, all these things the child may understand, but unless it is put to an application of solving a real-time question, it remains very elusive and it's very superficial. So the final form in which we can assess that whether the complete understanding has been achieved is actually proving a certain problem using all these basic things that we have derived. So I've just taken one simple example because I was taking congruence. So I've taken another example on congruence only. So you see that we were given a triangle where certain properties were mentioned, and we were to prove that they are congruent. In this we see we have used a two-column proof. So we have written certain properties that we observe here and the reasons for that. And finally we arrive using a criteria which is SAS congruence postulate. So this is the final form. The questions, we can have more complex questions around it, but that's the final form. So I'll just repeat the thing. The first is basic visualization and recognition, where you're just giving the material, they are just informally recognizing certain properties. Then they are describing what they have observed. Then the third is abstraction, where they are forming mental abstractions and informal abstractions. Then formal deduction, and then finally rigor. They are ultimately put to final solving of those problems. I hope it was a little quick for me. I know it's still a long video to go, but as teachers, if we apply these principles, and I have seen when I have applied these principles, children tend to understand what they are doing. And we know that children, if we can just ask very simple questions about basic concepts, we will realize that children carry very different meanings, and those different meanings become a hindrance for them to understand maths from a deeper perspective and from more refined perspective. So I really wish you all the best, and I hope that these videos are helping you out. So do write in your comments, and we'll come up with more videos which will be helpful. We'll take up these concepts which we believe that children find difficult, and we as teachers can play a significant role in helping our children out. Thank you.